in the school. It's a nice morning, so he's moving at a comfortable pace. After walking for 9 minutes, he's 6 blocks from home. All right, so that sounds like an ordered pair. All right, so you can kind of, like as you're going, make little notes. Like if you look at the x-axis, that's time. The y-axis is distance. Right? So normally it's x comma y. This time it's t comma d for any coordinate. All right? So x comma y under normal circumstances, but in this case it's t comma d. They use capital. So capital D. All right? So when they say he's, and the distance is in blocks, so we don't have to worry about any kind of conversions there. After working for 9 minutes, he's 6 blocks from home. So that's saying 9 comma 6 as an ordered pair. We could also put it in function notation, but we'll come up with that too. He stops to answer his a text on his phone from his mother. After 5 minutes standing still, it's a long text, he walks home quickly in 6 minutes to get a paper he forgot for school. All right. So at 9:06, he stopped for 5 minutes. So that would put him at 14:06 because he didn't go anywhere. He turned around to go home. We want to model it as a function of time. All right. So the first thing we do is we draw the graph. So he's walking to school. We did these function graphs back in Unit 4, but we didn't write the equations of them. We just kind of visualize what the scenario is telling us. All right. He's starting at home, comfortable pace, which means a steady slope. All right. So we're looking at that constant slope leading us to a certain distance away from home. All right. Then the distance didn't change for a certain period of time. That's weird. All right. And then after 5 minutes standing still, he walks quickly, or he walks home quickly in 6 minutes. So that gets us to the 20-minute mark. All right. But he's now back home. All right. So 20 comma 0. All right. So we have to answer a couple of questions, but then we have to model it over the time interval. All right. So how many blocks did Mateo travel before he turned back home? 6 blocks from home. He turned around and went home. So 6 blocks. That's easy enough. Now determine a formula for the distance he is from home, d, over the time interval 0 to 9. All right. So that's this piece. All right. It's a linear equation. But they want it d in terms of t. Right? It's still slope y-intercept though. Right? So normally it would be y equals mx plus b. Now it's d of t is equal to m times t plus b. All right? So instead of saying f of x, function of x, we're saying d of t, function of time. All right? So, but we still need a slope, we still need a y-intercept. So we're still going to approach this graph the way we just handled the very last one we did. Right? Find the slope, right? Find 2 clean points and get the rise over run. Check the scale on the graph, make sure they're not messing with you here. It looks like they're going by 1, so we can just count boxes, so that's fine. We have a clean point at the origin. The next clean point seems to be right here. All right, so that gives me a rise over run of 2 over 3. So my slope is 2/3. My y-intercept is 0. All right, so normally I would say y equals 2/3 x plus 0. I'm going to say here instead, d of t is equal to 2/3 times t plus 0. You don't have to write the plus 0. All right, but this is not true in all cases. It's only true if t is between 0 and 9. Now, once you read the second part, or the next part of the question, you realize hopefully where this is going. It's a contextual problem, but they're trying to get you to build towards the piecewise model. Determine a formula for the distance he is from home D over the time interval 9 to 14. So that's the second piece. That one's much easier. Start to look forward to things like horizontal lines. Horizontal lines have a slope equal to 0. Now you just have to look over to the y-axis to see what the y-intercept would be if that line extended there. It would be a 6. So the y-intercept for this, the extended line would be 6, so we say y-intercept is 6. All right. So then d of t would be 0t plus 6. Well, 0t is 0, plus 6 is going to be just a 6. If 9 is less than or equal to t is less than 14. And you have your last piece, which doesn't look symmetrical to the first piece. Would have been nice. And it looks like we're going to have an issue with the y-intercept, that it's going to run right off the graph. So we'll have to deal with that in a sec. But let's get the slope. All right, so I'm going to bring it right in here. Get 2 clean points. 2 clean consecutive points. This is nice. Slope is -1. That doesn't always happen. But the y-intercept, that's where we're going to... It's not really running into a problem. It's more like you just got to do a little extra work. Because if I follow the trend... Let me move this out of the way for a sec. If I follow the trend, it'll only get me so far. It'll get me right up to here. Now, unless you're one of those people that are like, all right, it looks like it's about 20. I think I'm good. Just going to go with it. I mean, there are plenty of folks that'll do that. Right? And if it's a multiple choice question, if it's something in the neighborhood of what you expect the answer is, maybe you get lucky. Right? We don't want to do that. Right? What we want to do is, now that we know the slope, is find how many points are in between where we are and where we want to be. All right? So that's 14 units. So that means we'd have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 steps in order to get back to the y-axis from where we are. All right? For every one of those 14 steps, we're going to increase our height by 1. All right? So since we're already at a 6, what that's going to do is it's going to take the 6 and add to it 14 times 1. All right? So the y-intercept for this part is going to be 6 plus 14 times 1. All right? The 6 is where you're at, the starting point, or starting height. The 4, let me zoom in. This is getting crazy. Number of steps to the x-axis. Y-axis, sorry. Number of steps up. Per unit. All right. And so that's a measure of the slope. We might say, well, why didn't I put a negative one there? Well, if we were going to the right, I would. But we're going backwards. So we have to change our value here. So that's why we're going up instead of down. Right? So my guesswork got me to a 20. It turns out it would have been right. It would have been a 20. But I wasn't going to take that chance. All right. And you could, honestly, you could also do the counting approach. You'd say, all right, well, the slope is the -1. I'm going to go up 1. So I'm at 14.6. All right. So then the next one would be 13.7, 12.8, 11.9, you know, and 10.10, and go that way, you know. So you can figure it all out in a bunch of different ways. It's just, you know, what's the most convenient way to do it, all right? So now we know our y-intercept, or what our y-intercept would be if we could actually get there. And there are algebraic approaches for doing it too. It's just numerically is a little bit cleaner. So d of t is going to be equal to -1t plus 20, so -t plus 20, if (14) is less than or equal to t is less than or equal to 20. All right, and then the last piece is just saying, well, what's the piecewise function, right? Well, we already did that work. Here's one piece. Here's another piece. And here's the last piece. It's just a matter of notation at this point. As long as you say d of t is equal to, rather than f of x or y or anything like that, you got to use the right notation, then you'll have it. All right. So yeah, I mean it's got a little kick to it, but it's definitely manageable if you follow the process. And you see, if you look at the next one, I'm not gonna go through the whole process with you. You know what? Maybe I will, because it's a weird topic. Yeah, I'll do it with you. Substantial snowstorm is hitting the northeast region and predicted to snow at a rate of 2 inches per hour. Actually, now that I think about it, this is a slightly different variation on the problem, so it's probably worth it to do it. A rate of 2 inches per hour for the first 3 hours of the storm. All right, so again, time against some other measure, in this case depth in inches. So when they say 2 inches per hour, they're giving us a measure of the slope. All right, so that's there's really no way to mark it up. I'll mark it up on the graph in a minute, but that's giving us a measure of slope. If you see the word per in the units of measure for a value, that's giving you a rate of change, which is a way of saying slope. That's over the course of the first 3 hours of the storm. So here's 3. 1, 2, 3. The slope, the rise over run, is going to be 2. All right. The assumption here is that there was no snow, there was no depth of snow initially. When the storm began, there was no snow on the ground, so that would be 0. Then up to over 1, up to over 1, up to over 1, until you get to the 3rd hour. Now I have the slope. M is equal to 2. They told us that. And the y-intercept is 0. All right, slope is 2, y-intercept is 0. The storm is supposed to pause for 3 hours. All right, so a little break in the storm. So until we get to 6, and just bring that down a smidge. that's a slope of 0. You think about in context, if it's a rate of change, if it's pausing, you're not gaining any snow. Right? There's no more snow coming down. It's constant. Whatever you were at in the beginning of the 3 hours, assuming the temperature isn't getting wonky, whatever the depth of snow is going to remain that way. All right? And so in this case, it is 6 inches. I mean, that should be enough for a snow day, I guess. Then resume at a rate of 1/2 inch per hour for the next 4 hours. So that would get us to 10. 1/2, rise over run, up 1/2. Oh, okay, thank you. Up 1/2, we have a slope of 1/2. And that's just simply because they gave it to us. Now you think about it based off of, like the last problem compared to this problem, they have to give you some kind of information for you to determine the slope. Whether they flat out tell it to you or they give you some points and you have to figure it out yourself. Either way, they got to give you something in order for you to make that determination. All right. The depth D of the storm. The depth of the storm. No, typo. The depth of the snow, right, is the total number of inches that has fallen at a given time. All right. So this looks like it only went for 10 hours. All right. So the graph goes out to 12. I'm just double checking. Paused for 3 hours. Next 4 hours. Yeah. So it only went out to 10. So it's going to stop right there. So we get a little extra graph that we're not actually going to use. Now we do need a Y-intercept for this last piece here. All right. So if I dial it back, down 1, left 2, down 1, left 2, down 1, left 2, that would get me to an assumed Y-intercept right here at 3. All right, so the Y-intercept here for this piece would be equal to 3. All right, now our 3 pieces, they span from 0 to 3, right? This interval here. Then it goes from 3 to 6, and then finally 6 to 10. All right. Now we could start answering their questions, but we're going to write the piecewise function also. How many hours is a storm? 10 hours. They gave us the units in the word problem, so I can just say, how many hours is a storm? 10. How many total inches of snow fell? That would be the last Y value that we have. Looks like 8. That might be a snow day with a follow-up 2-hour delay. All right. Determine a piecewise function. All right. Well, we have all the pieces. D of t or 2t, sorry, plus 0, so just 2t. That goes from 0 to 3. All right, starts off at 0, ends at 3. So if 0 is less than or equal to t is less than or equal to 3. All right. That's for the first 3 hours. Then the next 3 hours, so the period of time after the 3rd hour, but ending at the 6th hour, it has a value of 6 because we're looking at 0t plus 6. So if 3 is less than t is less than or equal to 6, that would give us the next 3 hours. And then the last piece, 1/2 t plus 3. And that would get us the rest of the way. So 6, for the next 4 hours. 6 less than t less than or equal to 10. Try to get as much of that on the screen as possible.